Okay, in this additional video, I want to talk about a few other aspects related to statistical analysis, which mainly focus on the statistical theory behind those analyses. So in this appendix, I will touch on three things. First, I will talk about maximum likelihood estimation and how it relates to ordinary least squares estimation, which we already got to know in the main lecture. Then we will see how a single theorem for the multivariate normal distribution can be used to derive almost everything belonging to contrast-based inference. And finally, I will show how to obtain the weighted least squares equation, which is applied in the case of non-IID errors. So you will remember that for ordinary least squares, the objective was to minimize the sum of squared errors. For maximum likelihood estimation, this is a bit different. Here, the objective is to maximize the log likelihood function. So since we are assuming normally distributed errors on top of the true signal in the measured data, our likelihood function, that is the probability of the data given the model parameters, is also a multivariate normal probability density function given by this first equation here. And the log likelihood function is simply the natural logarithm of this. If we then maximize the log likelihood function with respect to the model parameters beta, so the regression coefficients, and sigma square, so the noise variance, we obtain maximum likelihood estimates. And you can see that when comparing the beta hat estimator to the beta hat estimator from ordinary least squares, that these two estimates are equivalent. So with respect to the regression coefficients, maximum likelihood estimation leads to the same result as ordinary least squares. However, the estimate for the noise variance will be a biased estimate, which means that on average, it will not converge to the true value of the noise variance, and it needs to be divided by n minus p instead of n here in order to be an unbiased estimate. Okay, so with that, I want to come to the second part of this appendix, in which I want to go a bit deeper into the normal distribution and how we can use its properties to derive statistical inference for the GLM. But before I start with this, I want to just clarify terminology. So when we say that a random variable is normally distributed, or that it is following a normal distribution, all the following statements are equivalent. We can say that X is normally distributed with mean mu and variance sigma square, or X is a normal random variable with mean mu and variance sigma square, or X follows a normal distribution with mean mu and variance sigma square, or we can simply write formulas X tilde n mu sigma square, or we can write down probability density function or the cumulative distribution functions. And all these statements basically mean the same. What they mean is that when sampling this random variable, it will have a distribution which has this bell-shaped structure that you see on the right. And this bell-shaped curve is characteristic for univariate normal random variables. One can, however, also have multivariate normal random variables, which means that we are considering a vector with multiple entries, and all of these entries are following a normal distribution, and they are together following a multivariate normal distribution. Now, for the multivariate normal distribution, there exists the following theorem. Every linear combination of jointly normal random variables, or in other words, of a multivariate normal random vector is also distributed. So this is basically the most important theorem in all of GLM theory. And it's almost the only theorem that you need for understanding the GLM. This is not just joking. In fact, in my eyes, this theorem is so important that I will now put it into a speech bubble and put it into the mouth of Clippy, the Microsoft Office mascot until 2003. So what does the theorem say? The theorem says that if we have a random vector whose entries follow a multivariate normal distribution, this is given by the left part of the equation, and this multivariate normal distribution is characterized by some mean vector mu and a covariance matrix sigma. If we then multiply this random vector with a constant matrix and add a constant vector, we will obtain another random vector which again follows a multivariate normal distribution where the mean and covariance derive from the original mean and covariance and the constant matrix that we use to transform this original random vector. Here's an example for this theorem in action. So let's say that we have a bivariate normal distribution. For example, this could be activations, trial-wise activity levels from two adjacent voxels, which are somehow correlated and jointly follow a multivariate normal distribution with means mu1 and mu2 and some covariance matrix characterized by these sigma values. Then if we specify the constant matrix and the constant vector like this, if we obtain the transformation of this random vector composed just of two elements, this will be the difference between these two voxels' activity. And what the theorem now tells us is that the difference, because it is a linear transformation of the original multivariate normal random vector, will also have a normal distribution, in this case a univariate normal distribution because it's a scalar, where the mean and the variance can simply be derived from the mean and covariance of the original multivariate normal distribution. So now let's take this theorem or this insight and apply it to the GLM, the model which we are interested in today. So first we have the distribution of the errors. And in the beginning, I said that we are assuming independent and identically, so IID errors, which just means that our whole vector of error terms follows a multivariate normal distribution with mean 0, and the covariance matrix being a scalar multiple of the identity matrix. So sigma squared times IN. This is an assumption of our statistical model. Without this assumption, we wouldn't be able to do anything. Now, let's see how that assumption plays out in quantities that can be derived from these errors. So first, we have the signal itself, which according to our model is just a linear combination of the noise and something else. So here we have a random vector whose distribution we know. Then we have a constant matrix. It's here invisible because it's the identity matrix. And we have a constant vector which is added to this. So the result of this will be another random vector, which according to the linear transformation theorem has a multivariate normal distribution with mean x times beta, so the true underlying signal, and the same covariance as before. So from that, we can move on to the distribution of the parameters. Because in our ordinary least squares equation, the optimal parameter estimates are just a linear transformation of the measured signal. And we know the distribution of the signal. So we have a random vector, our observed hemodynamic signal. We have a constant matrix that it is multiplied with. And we have a constant vector that is added to it, which here is invisible because it is the null vector. This means that our estimates for the regression coefficients will again be another random vector following a normal distribution according to the linear transformation theorem. And if we work that out, we can find that the regression coefficient estimates follow this normal distribution with the true regression coefficients as mean, meaning that ordinarily squares parameters are unbiased. They, on average, converge to their true values. And that have a certain covariance, which has an interesting structure because it's just a product of the sigma square, the noise variance, times the design covariance. So x transpose times x and the inverse of that. In SPM, this is called BCOF, by the way. And it will become important for statistical inference later on. Because, again, we are moving this to the left. And now we know the distribution of the estimated regression coefficients. So we can have a look at the distribution of the contrast value, which again are simply a linear combination of those. So we here have a random vector, the vector of estimated regression coefficients, which is multiplied with a constant matrix, which in this case, at least for T contrast, is just a vector, contrast vector. And again, plus a constant vector, which is invisible because it's the null vector. This gives us another random vector, which in this case would be a scalar. In T contrast, the contrast value is always scalar. And if we apply the linear transformation theorem, we find that the distribution of the contrast values is like this. So it's again a univariate normal distribution with the true contrast value as the mean and the design covariance now transformed through this contrast vector as the covariance matrix. Once again, we are moving this to the right and now ask for the distribution of the test statistics, which are again a function of those estimated contrast values. So let's see what happens if when we divide the estimated contrast value by the square root of its variance. So the variance is the second part of the parameter in that normal expression. So we just take the square root of it and divide the contrast value by this. And if we do this and again apply the linear transformation theorem, which obviously also holds for univariate normal distributions, we obtain that this very simple normal distribution with unit variance and under the null hypothesis, which states that the contrast value is 0, this will be a normal distribution with mean 0 and variance 1. This is amazing because this is a standard normal distribution, the most well-known distribution, which would allow for very easy statistical inference. However, we are here dividing by the true noise variance. And the problem is that we don't know the true noise variance. We can only estimate it. So our next question will be, what will happen if we divide by the estimated standard error rather than the true standard error? For this, I'm introducing now a second theorem, but only very hand-wavingly, because very loosely speaking, it states that dividing a normal random variable by the square root of its estimated variance results in a T distribution with specified number of degrees of freedom. So without showing the proof for this here, you can read it up if you want. This T statistic under the null hypothesis follows a T distribution with n minus p degrees of freedom. The same can be done for the F statistic, where we will need a third theorem, which again, very loosely speaking, says that dividing a squared normal random variable by its estimated variance results in an F distribution with specific numbers of degrees of freedom. So once again, without showing the proof here, this functional form, contrast value multiplied with itself divided by the covariance of the contrast values, it follows an F distribution with degrees of freedom, with numerator degrees of freedom Q, that's the dimensionality of the F contrast, and denominator degrees of freedom N minus P, under the null hypothesis, obviously. So these are exactly the formulas that I showed you in the main lecture for the T and F statistic. And now you have some rough idea of where these formulas come from. One can use the linear transformation theorem for the multivariate normal distribution for yet another purpose, namely for obtaining the weighted least squares equation, which is applied when the errors are not independent and identically distributed. Remember that when we noticed that fMRI scans are usually serially correlated such that our IID assumption does not hold, we came up with a revised distribution of the errors, which said that the covariance of the errors is not a scalar multiple of the identity matrix, but it's a scalar multiple of another matrix V, which consists of several variance components, one corresponding to the white noise part and one corresponding to the colored noise part, which includes the autocorrelation of the fMRI signal. Now, the question is, how do we handle this model? We obviously can't apply the ordinary least squares solution because we don't have independent and identically distributed errors. And instead of minimizing the residual sum of squares, we need to minimize the weighted residual sum of squares. How does that work? So first, consider a matrix W such which is equal to the inverse of the matrix square root of the matrix V. If we use this matrix to left multiply the entire model, so we are multiplying the first equation with W from the left, we can see that we obtain different error terms whose covariance is sigma squared times WVW transposed. And because of the way we have defined this matrix W, this is a result due to the linear transformation theorem, by the way. Due to the way how we have defined the matrix W, this gives us a new model with independent and identically distributed errors, because the product W times V times W transpose just evaluates into the identity matrix. However, now in this equation, the signal and the design matrix and the errors have changed to those original signal design matrix and errors left multiplied with the matrix V, which is also called the whitening matrix because it transforms the colored noise into white noise, where we can then apply the ordinary least squares technique. So if we apply the ordinary least squares formula, because we now have a model with IID errors, it obviously uses the whitened matrix and signal X tilde and Y tilde. And if we work out all these equations, we can see that the result is very similar to the ordinary least squares equation, just that the weighted least squares equation has an additional inverse of V term inside the formula. Okay, so in the rest of the slides, you will find the reference which I used for creating those slides. You are, of course, very welcome to check those out. And with that, I want to say thank you and goodbye.